Okay, so when we talk about, if you start looking at communities, and on slide number 18, it's talking about an aerial view of the ground. And so you see all of these different patches and different, kinds of habitats, fields, shrubby areas, forest, lakes, whatever you see, you have what we call, you have certain habitats, different habitats. Now, if you look out behind the Cranberry campus, if you go out behind the Cranberry campus, you will see woods. And you say, why, we've got a forest back here. It's even got a little stream in there. But it's only about 30 feet wide, right? Or no, maybe 30 yards. It's not very wide. So if you were to say, I'm going to go deer hunting, I'm going to go get me one of them deer. Well, you're not likely to find one there because it's too darn small, right? A deer, even though they can live in smaller habitats, there is a minimum size to the habitat where they can live. And that's what we call a core habitat. Now, in the case of deer, we have them here in Pittsburgh where I live, but we do have little patches of woods that give them enough habitat. But there are species out there. One that we'll talk about later on this semester is the spotted owl. And I think it's the western spotted owl. Anyway, it's a spotted owl. It lives out west. And that darn thing requires huge amounts of acreage. 2,500 acres of mature forest is required for each pair of birds. And so they have a huge requirement for their core habitat. So deer, they can have quite a small core habitat, so they're not endangered in the slightest. But these spotted owls, they are, because they have, for one reason, because they have this huge requirement for a mature forest. So what about if we look at the distribution of individuals within some of these core habitats? So I'd said you might have a woodland area that's right next to a farm field or next to a lake, and it ends up you have greater biodiversity right on the edges and greater abundances right on the edges where two habitats come together. And what we call this is an ecotone. And it's because it gives them more resources. If you're a deer that is not very comfortable out in the open, you still will go out in the open on occasion to get some of that good grass right out there in that field. And then you can run back into your woods. And maybe you are something that lives in the open, but you say, well, there's that really tasty whatever, something that's just on the inside of this forest. I can just run in there and grab some of that too. So we have these ecotones, which is where communities meet. And it ends up, we had this phenomenon that I was talking about is something called the edge effect. And so we have the edge effect, and I think I have a video in here for you to watch. Somehow I don't. Oh, well. Anyway, I thought I did, but I don't. But anyway, I described it regardless. Okay. So we had said, we've had some terms, right? We had said diversity, that's the number of different species, and abundances are the number of individuals of any one species. And then we can talk about complexity. Now, don't confuse complexity with diversity. Complexity has to do with the number of different trophic levels. So if you think of, and the more complex a community is, the more healthy it is. So what that means is not only do you have the primary producers and the primary consumers, the deer eating the leaves, but you also have or mice, we'll say a mouse, field mice eating the grass, but you also have things like foxes or raccoons that are catching and killing the mice. That would be a secondary consumer. And then what else might you have? You might also have a tertiary consumer that's eating the mouse. So maybe a snake that's eating the mouse, that's eating the grass. These are trophic levels. And maybe even a quaternary level of trophic levels. If you had an eagle that eats the snake, that ate the mouse, that ate the leaves, right? So a complex community is one that has all of these different feeding levels, trophic levels. All right. So the more complex a community is, the healthier it is, and the more resilience it has. Another term, resilience is the ability of a community to come back to a similar condition after a disturbance. So around here, our forest is pretty darn resilient. So if you cut the forest down and you put in a farm, and 100 years later you stop farming, those trees, if nobody does anything with the land, if it's just left to sit there, it will gradually, over the course of hundreds of years, it will become forest again. That's what we're talking about with resilience. Low resilience means that you cut the forest down and it will never go back to that. That there's circumstances that will prevent that from happening. We'll talk about how tropical rainforests have very low resilience. If you cut down the rainforest and then you put cows out on it, and then you say, well, it'll come back. No, it won't. It's because most of the nutrients are in the plants and the plants are gone. There are some ways that they're figuring out of helping to bring them back, but they are what we call a low resilience community. So resilience is tied in with complexity. All right, so we have this thing. I've been using the term, I think I've used the term primary productivity before. And so primary productivity is the amount of energy that is captured by plants from the sun, right? And so that's the amount of energy. Now, the actual total productivity is really hard to measure because some of the energy that is used by the plants is used to feed, for the normal living circumstances of the plant. And so you don't really have any way to measure that. But there is something you can measure, and that's something, and we're on slide 19, and that's something called net primary productivity. And so what net primary productivity is the excess energy. So the plant uses some of its energy just to live, but the excess it puts into producing more plant. And so you can go into a community and, like a grassland community, and you can say, well, how much net primary productivity has happened here? You cut the grass and you go weigh it, and you say, well, we've got X amount of X kilograms of primary productivity per square meter. You can measure that. It's something you can measure. And I noticed here on this slide 19, I have something called stability there. Stability is really the same thing as resilience. The ability of an ecosystem to recover from disturbance, basically. All right, so 2 more slides. All right, so I'd used an example of an oak hickory forest, the kind of forest we have around here. And I'd said that if you cut the forest, it will come back, right? but it doesn't. So if you go to a farm field that's starting to convert back to forest, it's not immediately oak trees. No, you see shrubs. You see shrubs there and some smaller, dogwood trees, small trees that start coming in. And then if you go to another area that's even older than that, you'll get some different trees. And then if you go to an even older area, then you start to see the oaks and the hickories coming. And then after a while, after about 300 years, you get the oak hickory forest, and it doesn't change anymore. It's just what it is. And so that form of the community is what we would refer to as the climax forest. And we had said that we have this process of change, which is called succession. Succession is a series of different communities of species that occur during the course of going from a disturbed area to a climax forest. And we can talk about primary succession and secondary succession. So in primary succession, you get rid of everything. You got rock. That's all you got. And so if you start with rock, then the pioneer species that will come in will be like mosses and lichens. Moss is that little short green sort of a plant. And what they do is they break down the rock. And the lichens do the same. And they create the soil. And then once you get these soil in like the cracks, you start getting the plants coming in. And then you go again through this whole process of succession. And those early species, the mosses and lichens, they're what we call pioneer species. But that normally you don't start with no dirt. I'm talking rock only. If you have any kind of plant matter or dirt, it's going to be secondary succession. And it's going to, again, in both cases, it will lead to the climax forest. Okay. The final slide talks about disturbances. And I've mentioned these, and maybe I should have had this slide earlier, but a disturbance is any force that disrupts the established pattern of species diversity and abundance, or even community structure or community properties. So that's, fire is a disturbance, bulldozers are a disturbance, shopping malls are a disturbance, anything like that. It ends up, the one final point we have is there are some species that need disturbances. Out west, we have some communities where you have what we call fire-adapted species. And the chaparral communities out west in what we call the Mediterranean biome, basically what happens there is every year it's a shrub, it's going to drop its leaves and it's going to drop its seeds. But the seeds are really hard and they will not open. Now, one thing that's unique about the leaves is the plant puts turpentine in them. And you're thinking, turpentine? You mean that smelly stuff that burns? Yeah, that's it. So over time, the chaparral community drops all of these highly flammable leaves and these really tough seeds on the ground. And over the course of 20 to 40 years, eventually a lightning strike or somebody's cigarette butt lands out there and it burns off. And all of those seeds, 40 years of seeds, the fire is required for them to open. And they pop open, and any of the trees that may have been trying to grow in there were killed, but these seeds produce more shrubs. This is an example of a fire-adapted species. Okay, this is the end of chapter 3. All right, talk to you later.